South of Beersheba, the landscape empties. The Negev stretches to the Gulf of Eilat, 10,000 square kilometers of rock, wind-blown silt, and hardpan covering more than 60% of the country's total area. Annual rainfall in the Central Highlands averages about 100 millimeters, in the Deep South closer to 50. 100 millimeters of rain sounds survivable. It is not. The atmosphere above the Negev evaporates water at 3 to 4,000 millimeters per year, 30 to 40 times more than the sky delivers. For every drop that lands, the air takes back 40. The soil compounds the deficit. The northern Negev sits on a fine, wind-deposited silt that looks like it should be fertile, pale, mineral-rich, deep. But the moment rain hits, the particles seal into a hard crust. Water cannot soak in. It sheets off, carves flash flood channels through dry riverbeds, and disappears. Whatever moisture lingers near the surface gets pulled upward by evaporation, dragging dissolved salts along with it, and poisoning whatever tries to root. The plan, set in motion in the early 1950s under the direct mandate of David Ben-Gurion, was to farm this, not subsistence agriculture. Export-grade food production in a landscape where every physical variable, heat, evaporation, salt, soil, worked against growing anything at all. 4 interlocking systems built across 5 decades turned a place where the air drinks 40 times what the sky delivers into one of the most productive farming regions on the planet. In October 1946, a group of settlers established Kibbutz Hatzerim on a barren hill in the northern Negev, just west of Beersheba. The site had one acacia tree. The soil was the same wind-deposited silt that blankets most of the region, crusted, saline, bone-dry. They tried what farmers have always tried: flood the fields. Apples, peaches, sugar beets, alfalfa. You can understand why they thought it would work. The silt contains real mineral nutrients locked inside it. 2,000 years earlier, Nabatean engineers had farmed this same desert by channeling flash floods into stone-terraced plots. Proof that the ground could produce if the water delivery was right. But the Hatzerim settlers used a different delivery method. Under the Negev's extreme heat, summer temperatures regularly pushing past 40 degrees Celsius, every liter of surface water vaporized fast, and as it left, it wicked, dissolved salts upward through the soil the way a sponge draws water from a dish. Within a few seasons, the topsoil was white with mineral crust. They tried flushing, flooding the fields with imported fresh water, draining them, hoping to push the salts below the root zone. It worked for days. Then the sun pulled the salts right back up. The process meant to fix the contamination was accelerating it. By 1959, the community was debating whether to abandon the settlement entirely. Here's why. Every conventional irrigation method, flooding, furrow, sprinkler, delivers water to the soil surface. In a temperate climate, most of that soaks in. In a landscape where evaporation outpaces precipitation by a factor of 30, delivering water to the surface is functionally the same as pouring it into the air. And in saline ground, every liter that evaporates leaves its dissolved minerals behind, compounding the poisoning with every cycle. At the national level, the mismatch was geographic. 80% of Israel's rainfall landed in the narrow northern third of the country. The southern two-thirds, where the open land for agriculture existed, received almost nothing. International proposals to share the Jordan River basin, including a 1955 American brokered plan allocating water among Israel, Jordan, Syria, and Lebanon, collapsed when the Arab League rejected them on political grounds. Cooperative water management was dead. Military conflicts over upstream diversions followed. The challenge facing the planners was not agricultural. It was thermodynamic, hydraulic, and geographic. 3 simultaneous engineering failures locked inside a single landscape, each reinforcing the others. The soil sealed itself against rain. The atmosphere stole whatever moisture arrived. The salt poisoned whatever managed to root. And the nearest reliable freshwater sat at the bottom of a geological trench 213 meters below sea level, over 100 kilometers to the north. Fix anyone. Variable alone, and the remaining 2 still killed the crop. Between 1953 and 1964, over 4,000 laborers attacked the most fundamental constraint: distance. Israel's largest freshwater body, the Sea of Galilee, sits in the Jordan Rift Valley, more than 200 meters below sea level, the country's largest natural freshwater body trapped at the bottom of a continental fault line. Gravity-fed flow was physically impossible at the source. Instead, four massive pumps at the Sapir station forced the water up a 2,200-meter steel pipe, lifting it 257 vertical meters to an elevation of 44 meters above sea level. To put that differently, the energy required to push that much water up, that much rock, consumed 100 megawatts, roughly 2% of the entire nation's electricity output. From the ridgeline, the water moved south through open channels, through a tunnel blasted 6.5 kilometers through the Sumerian hills, and through inverted siphons that used the physics of communicating vessels to push water down into ravines and back up the opposite slope without additional pumps. At peak capacity, the carrier delivered 1.7 million cubic meters of water per day. But arriving water was not usable water. The moment it touched the Negev silt, the old cycle restarted: evaporation, salt migration, crust formation. The carrier had solved geography. It had not touched the physics of how water meets soil in extreme heat. It comes down to one variable: the point of contact. In the early 1930s, decades before the carrier was even conceived, a water engineer named Simcha Blass noticed a single tree thriving in a farmer's dusty yard, far taller than anything around it, growing in ground that looked completely dry. Blass dug beneath the surface and found a faulty pipe coupling, dripping water in a slow, steady rhythm directly into the earth. That defect is the whole story. Beneath the bone-dry surface, the constant drip had formed an onion-shaped bulb of saturated soil, an expanding pocket of moisture that kept the roots continuously hydrated while the surface stayed dry and the atmosphere above never had a chance to steal. Every irrigation system in human history had delivered water to the surface. The surface was exactly where it should not go. Blass spent 3 decades developing a device that could replicate what that leaking coupling did. The challenge was mechanical. Early prototypes used tiny pinholes in plastic tubing, which clogged almost immediately with sand and mineral scale. Blass's solution ran against instinct. Instead of making the opening smaller, he made the internal passageway wider and much longer. He molded a winding labyrinth inside a plastic housing. Water entered at pipe pressure and exited as a slow, regulated drip. Its energy dissipated entirely by friction against the labyrinth walls. The channel was wide enough that sand and particulates flushed through without blocking. What happened underground was more important than what happened inside the dripper. A single outlet, releasing water at a steady low rate, formed an expanding onion-shaped moisture zone beneath the surface. 3 layers emerged within it: an oversaturated core near the outlet, a well-aerated middle band where roots thrived, and an outer boundary where all dissolved salts accumulated, physically pushed outward by the continuous pressure of incoming water. The toxic salts that had destroyed Hatzerim's flood-irrigated fields didn't vanish. They were relocated to the perimeter of the wet zone, permanently separated from every root. The same silt that killed crops under flooding became productive under drip, not because the chemistry changed, but because the geometry of water delivery kept roots and salt apart. Farmers could also dissolve fertilizer directly into the drip line, delivering precise nutrients straight to the root zone without losing a molecule to runoff or surface evaporation. In 1965, Blass partnered with Kibbutz Hatzerim to manufacture the first commercial plastic drippers. The settlement that the desert had nearly killed became the factory that built the tool to farm it. But growing food required more water than the country possessed. Drip cut waste at the delivery point, but the total national supply was still being divided between cities doubling in population and a desert doubling in cultivated area, and it wasn't enough. Rather than rationing, the engineers closed the loop. South of Tel Aviv, the Shafdan facility began capturing the sewage of more than 2 million people, roughly 130 million cubic meters per year. After initial biological treatment, the water was flooded into open basins on the coastal sand dunes near Yavne. 1 day flooded, 2 to 3 days drying. The drying cycles forced atmospheric oxygen deep into the sand, keeping native bacteria active and alive. The water then percolated downward through 30 meters of sand, spending an average of 300 to 400 days underground. None of that cleaning involved chemicals, no chlorine, no synthetic disinfectant, just sand, bacteria, oxygen, and time. By the time the water reached the recovery wells, it had been stripped of pathogens, organic contaminants, and suspended solids. It was piped directly to the Negev for unrestricted crop irrigation. But recycling what cities discarded still depended on the cities having clean water to use in the first place, and that supply was still tied to rainfall. Five massive desalination plants, constructed along the Mediterranean coast between 2005 and 2015, severed the last dependency. Advanced energy recovery devices captured the kinetic force of the high-pressure reject brine and recycled it directly into the incoming seawater, slashing energy consumption to a fraction of what earlier thermal methods demanded, and dropping the cost of synthetic freshwater to roughly 40 cents per cubic meter. These five plants now supply over 75% of the nation's domestic drinking water, which freed virtually all the natural freshwater, all the recycled sewage, and all the aquifer reserves for a single purpose: feeding the desert. The four systems formed a single closed circuit. Desalinated seawater supplied the cities. City sewage filtered through 30 meters of coastal sand. The filtered water irrigated the Negev through drippers that displaced salt away from roots. The ocean had become the source. The city had become the treatment plant. The desert had become the farm. For the first 11 years, the landscape showed nothing. Tunnels were being blasted through hillsides, pumping stations poured into bedrock, all under tight security to prevent Syrian sabotage of the northern intake. Desert settlements survived on emergency pipelines and ration truck deliveries. It was not a promising start. The convergence arrived in 1965. The carrier began pushing sustained volumes south at precisely the moment Netafim shipped its first commercial drippers. The effect was immediate at the field level. Irrigated land expanded from roughly 30,000 hectares in 1948 to nearly 200,000. Farms abandoned failing subsistence grains and pivoted toward high-value produce: peppers, melons, cherry tomatoes, medjool dates, crops that thrived under intense desert sun once drip removed its ability to steal the water. In the Arava Valley, one of the hottest and driest corridors in the country, farmers discovered that drip geometry allowed them to irrigate with brackish local groundwater that would have killed crops under any conventional method. The salt displacement kept the root zone clean. And at the outer edge of the wet bulb, the controlled saline stress concentrated sugars in the fruit. The desert's most hostile variable had become a production advantage, and then the grid started attacking itself. 20 years into the Shafdan operation, farmers across the western Negev reported a crippling failure. The friction labyrinths inside their drippers, the exact mechanism that made desert agriculture possible, were filling with a thick, impenetrable black sludge. The source took years to trace. Deep inside the coastal aquifer, beneath the Yavne sand basins, the organic load from decades of infiltrated sewage had consumed all available oxygen in the sand, creating oxygen-depleted zones where none had existed before. In those zones, naturally occurring manganese in the rock dissolved into the groundwater. Manganese migrates slowly, it adsorbs to sediment grains, saturating the sand particle by particle, taking 10 to 20 years to reach the recovery wells. When the manganese-loaded water was finally pumped to the surface and entered the oxygenated pipeline, it oxidized instantly into a dense black precipitate that sealed the dripper labyrinths shut. The mechanism that made the desert farmable was being disabled by the water supply that fed it. Chemical treatment at a flow rate of 130 million cubic meters per year was financially impossible. Engineers designed a filter bed coated with the collected manganese precipitate itself, turning the contaminant into its own catalyst, stripping dissolved manganese from the water using nothing but atmospheric oxygen before it reached the pipeline. It was a quiet fix, given the scale of what it protected. A second consequence remains open. Reverse osmosis membranes strip everything from seawater, including magnesium, which natural freshwater from the Sea of Galilee had always provided. As desalinated water replaced natural water in the cities, and city wastewater fed the Shafdan, and the Shafdan fed the desert farms, magnesium levels in diagnostic citrus leaves across the Negev dropped by nearly 30%. The mineral deficit cascaded from the water through the soil into the food. Epidemiological studies linked the gap to measurable increases in cardiovascular risk, a consequence no hydrologist had modeled when the membranes were specified. The machine that started as a water project had become a soil chemistry project, a materials science project, a public health question, all running on the same grid, all requiring continuous recalibration. By the 2010s, the integrated system had crossed a threshold that would have been unthinkable to the settlers who debated abandoning Hatzerim in 1959. Israel had moved from chronic water deficit to structural surplus. The question was no longer whether the desert could produce food. It was what to do with the water the system no longer needed. The statistics arrived from different decades and different scales. Tomato yields in the Negev reached 300 tons per hectare, 6 times the global average of 50. Citrus production hit 262 tons per hectare, outpacing both North American and European benchmarks. Overall agricultural productivity by 2004 was 1,600% higher than 1950. For context, Israel currently recycles 85 to 87% of its treated municipal wastewater for agriculture, the highest rate on the planet by a factor of 4. The next closest country is Spain, at roughly 20%. Every shower and flush toilet in Tel Aviv eventually feeds a drip line in the desert. The Arava Valley, the deepest, driest corridor in the country, stretching south along the Jordanian border toward the Red Sea, now produces 60% of Israel's total fresh vegetable exports. Over 40% of the country's total crop output grows in soil that receives less than 100 millimeters of rain per year, and the infrastructure delivered one final reversal. By 2023, the desalination surplus had grown large enough that engineers spent roughly $1 billion shekels to reverse the national water carrier. The pipeline that spent 60 years extracting fresh water from the Sea of Galilee now pushes desalinated Mediterranean seawater backward, uphill, inland, and discharges it through the Zalman stream at 5,000 cubic meters per hour, directly into the lake. For the first time in decades, the water level moved in the right direction. The extraction engine had become a replenishment engine, stabilizing the lake through multi-year droughts and even enabling the country to double its water exports to neighboring Jordan. One faulty pipe coupling in a dusty yard. One tree that shouldn't have been growing. From that observation came a dripper, then a factory at a failing kibbutz, then a national hydraulic circuit that routes the Mediterranean through a city's plumbing, through 30 meters of coastal sand, and out of a plastic nozzle at the base of a tomato plant in a desert that now outproduces countries with 10 times the rainfall. The physics of the Negev never changed. The soil still seals, the air still drinks, the salt still rises. What changed was every point of contact between the water and the ground. 4 systems, each closing a different failure point, none sufficient alone. The carrier moved volume across geography. The dripper changed the geometry of delivery. The sand dunes cleaned what cities discarded. The membranes severed the last dependency on weather. None of them changed the desert. Together, they hold it in continuous production, not a green miracle, but a maintenance schedule that never ends. If that kind of engineering interests you, subscribe. More is coming.